Hello everyone, welcome back to the class on Principles of Communication Technology. In the previous two sections, we explored the characteristics of baseband signals from different perspectives, such as baseband signal waveforms, commonly used baseband signals, and their applications. In this section, we will discuss the transmission of baseband signals. Students, this is a typical block diagram of a baseband signal transmission system. It takes the input signal and performs symbol mapping, which is essentially a form of encoding. Since rectangular pulse signals have a wide frequency spectrum that is not suitable for transmission, they are passed through a band-limited pulse-shaping sending filter, transform the transmission code into a baseband signal waveform that is suitable for channel transmission, and then it enters the channel for transmission. In baseband transmission systems, the channel is usually a wired channel. Why is that so? Can't wireless channels transmit baseband signals? Due to the high frequency characteristics of wireless channels, modulation is typically required for transmission. Baseband signals usually use twisted pair cables or coaxial cables. Since the transmission characteristics of the channel cannot meet the conditions for distortion, free transmission, it can cause distortion in the transmitted waveform, and noise is also present. The receiving filter is used to receive the signal and filter out noise and other interference as much as possible, equalize the channel to make the output waveform conducive to decision-making. Bit timing pulses are used for synchronization and sampling decisions, ultimately recovering the original information. In our diagram, the 7th symbol has an error. Why did an error occur?
An error means that the wrong symbol was received.
Why did that happen? The most direct reason for errors is incorrect decisions made during sampling. The main reasons for incorrect decisions are twofold. One is intersymbol interference. Is it where symbols from neighboring bits interfere with each other? It's similar to two students sitting close together, and their arms bump into each other. The other reason is additive noise in the channel. We've discussed additive noise before.
But why would neighboring symbols interfere with each other when they are sent one by one according to the timing?
Let's take a look at intersymbol interference. Intersymbol interference, or EC in short. We'll also learn about this concept when we learn about mobile communication technologies. EC refers to distortions that lead to widening of the waveform and creates long tails in the waveform of the preceding symbol, spreading to the sampling decision of the current symbol, causing interference in the decision. Therefore, EC is caused by changes in the waveform during the transmission process. We can see the waveform changes caused by EC in an example. B-band represents the information bits to be transmitted. AN represents the selected bipolar codes, and they are transmitted through a sending filter. The red waveforms below are the waveforms of each symbol, and they interfere with each other, leading to waveform widening. Therefore, the purple waveform is the composite waveform transmitted in the channel, and because EC is not significant, we can see no errors in the decision made at the receiving end. In our previous discussion, we qualitatively examined how a baseband signal transmission system operates and gained a practical understanding of intersymbol interference, EC, and the influence of noise. Now, let's delve into a quantitative analysis considering both the time domain and the frequency domain. First, let's begin with our analysis model. Binary baseband signals correspond to dt, and we can express the total transmission characteristic omega of the system, along with its unit impulse response. The baseband signal undergoes various transformations, somewhat like a journey with numerous challenges. Ultimately, it results in yt, which is subsequently subjected to decision, making to determine whether it represents a 1 or a 0. Now let's examine the receiving filter, which outputs a signal yt and can be represented in this form.
Why is it a summation formula here? Isn't this a single symbol?
We've just analyzed that the transmission in the channel consists of synthesized waveforms, which spread to the preceding and succeeding symbols. Now, let's quantitatively calculate how to eliminate intersymbol interference. Easy in this formula. We've also added noise, nRT. Do you understand?
Oh, I see now. I'll contemplate it further after class.
Alright, let's continue our analysis. The sampling detector performs sampling and decision on yt, where t0 is the delay time. Let's write its sample values. Looking at this formula, the first term is the sample value of the desired received symbol waveform. The second term is the intersymbol interference, and the third term is noise. Obviously, only when the intersymbol interference and noise are small enough can we ensure the correctness of the decision mentioned above, otherwise, it results in errors. So, how can we eliminate intersymbol interference without considering noise? Can anyone explain?
Let me think for a moment.
When the second term is equal to 0, t here is no intersymbol interference. Easy, right? You explained it very well. It's impossible for the waveform of the preceding symbol to reach 0 at the sampling instant of the succeeding symbol. For example, let's look at this graph. Because there's tailing phenomenon in real symbols, we need to make a requirement on the waveform of the preceding symbol, which means it reaches 0 at the sampling instant of the succeeding symbol. TB and 2 terabytes are sampling times for other symbols. We can see that the waveform is at 0 at these moments, so it won't affect other symbols. For example, let's look at this graph, which is the condition of no intersymbol interference in the time domain. In this formula, what does it mean? It means that the sample value at the instant of this symbol is non-zero, while the values of other symbols at this sampling instant are all 0. Next, we analyze and process this through frequency domain based on the relationship between time domain and frequency domain, which can be mutually Fourier transformed, converting an integral relationship into a sum of segment integrals. Each segment is TB divided by 2 pi. After analyzing this and using the time domain condition, we can obtain the frequency domain condition. We won't go into detail about the derivation process here. This condition is a method to test or design whether the transmission system will produce intersymbol interference. Its physical significance is that after cutting, shifting, or superimposing, the result is a constant. Here, the constant is TB. This frequency condition is a theoretical basis for testing whether the transfer function can eliminate intersymbol interference. Through an example, we illustrate cutting, which means figure A becomes B, C, and D through shifting and superimposing, and the final result, according to the previous analysis, the design of a transmission system. Without intersymbol, interference can start from two aspects. One is an ideal low-pass characteristic, which means designing an ideal rectangular filter. At this time, its bandwidth is 2 terabytes, and we call this bandwidth the Nyquist bandwidth. The symbol rate RB is equal to twice fan, which is called the Nyquist rate. At this time, the bandwidth utilization is 2 baud per hertz, which is the limit of what a baseband system can achieve. And its physical meaning is that it can transmit 2 symbols per hertz. Furthermore, we can also calculate the data transmission rate. Although it's impossible to achieve this ideal low-pass signal, but this waveform is actually impossible to achieve in practice, because its transmission characteristic shape an infinitely steep transition band, which is impossible to achieve in engineering. Even if such transmission characteristics are obtained, the tail decay characteristic of the impulse response waveform is very poor, decaying at a rate of only 1. To solve the difficulty of designing an ideal low-pass filter and still achieve intersymbol interference, we can use cosine roll-off systems. As long as the amplitude characteristics are odd symmetric at the center frequency in the roll-off section, we can also achieve intersymbol interference free transmission. At this time, we call alpha the roll-off factor, and the bandwidth B is equal to Fm plus F delta. The bandwidth utilization is 1 plus alpha divided by 2. When alpha increases, the bandwidth also increases, and the bandwidth utilization decreases. RB is the symbol rate, and if it's a multi-level modulation system, the bandwidth utilization is the formula as follows. The meaning is also the maximum number of bits that can be transmitted per hertz of bandwidth. We can see the different roll-off characteristics and their response curves in the figure below. When alpha is larger, the tail of its curve decays faster. When alpha equals 0, it's an ideal low-pass case. At this point, we can see that the bandwidth utilization is 2 bauds per hertz. When alpha equals 1, it represents the spectral characteristic of a raised cosine. And what is the bandwidth utilization at this point? Take a moment to think. The answer is that the bandwidth utilization is 1. Cosine roll-off filters have the characteristics of being easy to implement, rapid convergence of response curves at the tail and a small overshoot, making them suitable for strict timing requirements. However, the cost is increased bandwidth, resulting in reduced bandwidth utilization. When alpha equals 0, it corresponds to the ideal low-pass case, and when alpha equals 1, it represents the raised cosine situation mentioned earlier. Now, let's compare the characteristics of ideal low-pass and raised cosine roll-off for high bandwidth utilization. It's difficult to achieve and has slow convergence of the response curve at the tail. For low bandwidth utilization, it's easy to achieve and has faster convergence of the response curve at the tail. So, can we combine the advantages of both systems? The answer is to use partial response techniques. This is what we will discuss in the next class. Finally, Let's pose a small question for you to practice. In this graph, we need to see if it can achieve intersymbol transmission without interference. Then calculate the row-off factor, system bandwidth, the highest symbol rate without intersymbol interference, and the bandwidth utilization. After you've completed today's assignment, you can upload it to the discussion forum. That concludes today's content. Thank you everyone and goodbye.